So a search function, basically, we're drawing it, follow this particular look on the y-axis and the x-axis. It will look like this, where we're going, surging up, coming down, and then going into a zero over here. Now, this kind of a function will always have a 0 and a 0 coordinate to start with. And it will look like this. Fx is equal to function that is used. And we use it in medicine, and we also use it in radiation, for instance. So what are some of the properties of this particular function? You can see that it has a maxima here, and this maxima come at a point. It will also have another point here, which will be its point, and this is going to be 2 over b. Now, you might notice that in that case, can you actually see that the distance here is exactly the same from here to here, okay? The other things that you want to look at is this bit over here, that this part here, we will call that a concave. Concave. And this part over here, all right, we'll call this bit convex. At the point of inflection, the x value is 2 over b, and the y value is also known as 2a over b e squared. Okay, so search functions always pass through the origin. Why? Because if you're looking at this particular function, ATE minus BT, and if you substitute this T here for 0, you get A times 0, E to the minus B times 0, and that gives you 0. So the input 0, the output is 0. So now we'll go to a problem. So let's pretend, here we've got an example, okay, and I'm going to write this down so that you're done. We are told that regression, this is the question, regression analysis, and I don't know whether you actually did regression analysis, but we used to do that, and was it done in year 11 and 12? Yeah, regression analysis produced, because students then used to have a set of data which produced this kind of a function, but we go straight to the function. So regression analysis produced a model for the radiation levels around a nuclear disaster. Okay, site. And this model is given by a radiation at a given time, and the time here will make it in days, okay? In microsieverts. I don't remember whether we spelt it. I remember doing this in physics with you, okay, but radiation is in microsieverts, okay. So this model is showing me this. This is the equation that it's modeled by. 45 T E 0 minus 0.4 T. Now, the question here that we're going to be starting to ask is A. So the question here is, I'm going to show, first of all, first of all, before you write, I want to talk about that too, but I'm going to first of all show that derivative of this function is given by and this will be the derivative of the function. And usually this is what you will be asked to do. They'll give you the derivative and say, well, please show me how you did that, which is pretty cool because it's one way or another, you're going to get to it, right? E to the minus 0.4t. Now you might want to do, and the thing is, they want to explain, okay, explain what is the purpose of the derivative. So if you've got a piece of paper there, let's see if you can show me that you've actually can do that derivative.
In the sign diagram?
Where's the 18 from?
No, yeah, purpose of the derivative. Exactly. You want to show this. All right? So let's go and see if we can show that. You know that you're going to use the product rule in here for these particular search functions. We're going to use the product rule, and that is because RT, okay, is initially 45t, e to the minus 0.4t, which means that we've got two t's here. We've got this and we've got this. So what we're going to do is we're going to do the usual thing, and we're going to say that means that u, therefore, is 45t, and u dash is equal to 45. We're okay with that, aren't we? Mm-hmm. And v is equal to e to the minus 0.4t, and v dash is equal to e to the, no, I'll put it the way I had it, then 4t, which is going to have to be multiplied by minus 0.4. Okay? Now, having done that, usually do write this down, because I like to do that, and I think you do too, is that we actually write u dash v plus u v dash. So now we just substitute this. That's the 45. You okay with that? Yes? All right. And v is equal to, so far I'm not doing anything that's really hard, am I? I mean, and then u is 45t, and v dash is e to the minus 0.4t. Now, that's okay, but what we've got to do at this moment, that's just the elongated part. Okay, that's r dash, right? So, all right, so now we've got to change that into, show it that it's this, correct? All right. So can we do that quite easily? I would go leave, because I've got already 45e that, so I'm going to leave that here as it is and say that's 45e to the 0.4t. Okay, and now I need to show, now I want to go here and I'll multiply the 45t with the minus 0.4, and that's actually minus 18, correct? Yeah. Minus 18t e to the minus 0.4t. And because I've already written plus and minus here, I'll just rewrite this again. And this is what they wanted.
Miss, you have a t next to the 18.
18, sorry? Oh, when I show the derivative, oh, thank you. So I didn't copy that correctly, did I?
Oh, so the answer does have a t?
Yeah, the answer has a t. Obviously, I didn't show that it is, you're right, okay? See, sometimes you get this, I'll put that t now here, so that...
Otherwise you would have 45 take out 18 and that wouldn't
Yeah.
work.
Sorry about that. Thank you, Charles, for that. That's exactly what I want to hear from people, okay? That's really good. Now that I have that, so we want to explain its purpose and its derivative. So what am I going to say? That's what they wanted to show. So now that I actually proved that it is the derivative, I'm going to need to understand what it is in that context. So it means. So I want to show it in that context. What does it mean? It means that this is the rate of change. Okay? These words are so important. The rate of change, okay, per day, because we'd said day, at a given time. At a given time, increasing
The change in the rate.
or decreasing its rate of change.
So we don't know if it's increasing or decreasing yet.
That's because we're talking about the overall thing in the radiation level.
Okay.
And it is both, isn't it? Just from the graph, you can see that it's both increasing and then it is decreasing. So it's increasing and decreasing. Okay, so now that we have some understanding, what we're going to do is number B. And that thing is we're going to explain the features that suggest that this is a surge model. This is where I'll explain this, okay? So now the question says explain the features that suggest that this is a surge model. Okay. So these radiation levels can take a form of different functions, but we need to decide. It may not be. It might be a polynomial function that it takes form. But so we've got data that we put together and then we graph it and say what's the best fit. And it seems that it best fits this model. Have a look at this one. If we've got RT and the model that we have is 45 T E minus 0.4 T, and our model, okay, is A T E minus B T. All right, so what have we got over here? What does the 45 shows you? That's the position of the constant. Position of constant. So we know that. Did you want to say something about that, Vince?
No, I was just curious what does it look like if you factorised it earlier on, the second,
Oh,
the
okay.
first derivative, that's all.
All right, then we've got the t value here. Then we've got the e value here for both of them. Can you see? They're in both parts. So we've got the e value. And we've got the constant which has a negative operation here. This is the constant. Constant with negative operation. And negative, I'll write that operation. Negative operation. And what else do we have? And we've got a t value here, okay? So both of them, all of these really fit in really quite well, correct? And, and t here. Okay, so, and also t occurs twice. So you know that this is a surge. T occurs twice. It's a little bit unlike the logistic model, which also has a limiting factor. We don't have that limiting factor over here. So now to the third question, this is going to be, I suppose, really easy. Now find the time at which radiation was at a maximum. And I'm going to just add to it, because sometimes questions are like that, and find the exact value of maximum radiation. So in this particular thing, how do we find the time at which radiation is the what do we call it? At the maximum.
We get the first derivative.
If I just draw this back over here, where does it happen? Up here is the maximum. All right. And what did I say? So when I want to find the time, where is the time? The time is on the x-axis. Okay, the time is at the x-axis. And what did I say that this is? 1 over b. All right, so if it's 1 over b, that occurs at time 1 over b. We know that the maximum occurs at time 1 over b because of those properties of the search function. So we can say now that the radiation maximum is at 1 over b, at time 1 over b. Can you identify what the part of b that we need for this function? Where is the b part? Okay, so if I had a look at this part here, t, e to the minus 0.4 t, it's really important that you know that we are using, okay, this is 0.4 is the b, okay, not the negative. So please remember that, okay? So b is 0.4, not negative. No. So make sure you remember that. So that means that t is equal to 1 over 0.4. Now, if I want to find out the exact value, okay, don't plug it into the calculator, because this will not give you the exact value. We now have to do it like this. So we will go into, this is actually another way of saying 2.5, but 2.5 we don't use because that's a decimal. We can use 5 over 2, but in here I'm going to, this is also a decimal, but because it's 0.4, I'm going to use this particular decimal because I think it'll be okay. So I could write down, or I could write down as this, 5 over 2 is equal to 45, 5 over 2, e to the minus 0.4, oops, sorry about that, because this is going to, see if I can actually move this. No, just move that. Okay, I can't. And then I'm going to multiply it by 5 on 2.
Just take 5 halves away. Elizabeth, take 5 halves away.
Okay, so 45 times 5 is 225. 225 over 2, e to the minus 1. So that is the exact form. Okay, I could do that. 225 over 2e. That's the exact form. But if we want to find out exactly what it is, because we want to have an idea, okay, that'll be 41.4 sig something or other. So the next, correctly, of course, you can go up to the graph function of the calculator and type it in. So let's go and get our calculators down. All right, I'm typing now. At what time
Was the rate for math?
Thinks he could do.
does the radiation decrease at the fastest rate? All right, so you know that this is a search function, fastest rate at the point of inflection. Really note that over here, how would you describe that? This is the fastest rate of decrease, okay? Fastest rate of decrease. And over here, where I'm showing you the arrow, this means that it decreases, it also decreases, okay? But do not forget to say that it decreases at a, what kind of a rate? Increasing rate. Increasing rate. That's really important, okay? And in here, it decreases also, but it decreases here at decreasing rate. And this is where it is concave and convex, okay? So we've got these two. So what are other properties that we want over here? So in that case, we do know, though, that this was 1 over b. This was what? 2 over b. Okay, so at least we know that this is 2b. This is time. At what time does the radiation, how do you work this out? Time is 2 over b. Charles? So, no. Time is 2 over b. This is where the rate of decrease is the fastest at that time, okay? That becomes 2b, which then is 2 over, what was b? 0.4. Okay, so we know that. Do that, that becomes 5 hours. No, 5 days.
You just doubled in the 2.5 from before.
That was enough, okay? But you did that over here. So it's
Just doubled the other hours.
5 days. Now we go to the next one, which is when will all the acceptable radiation level be reached if accepted radium level is 0.037. So acceptable level is 0.37 Siegerts. Now, when will this be reached? When will this be reached? The only way you can do it, you do not solve it algebraically because there are 2 t's. We can't do it. You do it on the graph. You've already got the graph. Now all you need to do is so just put y is equal to 0.037.
In your G-solve,
And then
go to G-solve and find out the y value, put that in there.
so draw
Because otherwise there won't be.
line y is equal to 0.37 G solve for intersection. And what did you get? The answer is 19 days? 19.4 days?
So where is it? Shift G-solve.
After 19.4 days. Yes? Okay.
0.33.
I just want to finish off, Vince, okay? So basically you're saying that after 19.4 days, people can go back and be relatively safe under the health guidelines, okay?